and welcome. Just as in walking, one of the hardest things in proton NMR is the first few steps. I'm going to take you by the hand and be your guide. My goal is to teach you how chemical shifts come about, how to define chemical shifts, how memorizing a few chemical shifts can help estimate others. A superpower is being able to predict the number of resonances a molecule should have, combining symmetry, integrals, molecular formula, double bond equivalents, DBEs, and a convenient way of assigning structures to unknowns that brings all this stuff together. Let's start with a little bit of NMR theory, shall we? I assume you already watched my 13C NMR video. That helps a lot because spectra in carbon NMR are easier to understand. If not, the link is down under. Nuclei spin state a half, split into two levels, aligned or opposed. Energy differences between these two levels are tiny and proportional to the strength of B0 applied. Boltzmann worked out how to calculate population differences between low and high energy states. He produced this equation and then he committed suicide. So we won't derive that equation here. NMR spectra plot where magnetically inequivalent, that means different types of protons in the molecule, resonate. We'd like to standardize the scale so that different spectra measured on different spectrometers having different magnet sizes, B0, have the same types of pattern. How should we do that? We do it by defining another parameter, the chemical shift, delta. Chemical shift is the resonating frequency of the proton we're observing minus the resonating frequency of a reference compound, all divided by the resonating frequency of the reference compound. Chemical shifts, delta, have no units. They're just the ratio of two frequencies. Frequency differences for different resonances in the same molecule are small compared to the absolute frequency. So chemical shifts are measured in parts per million, a million, where 1 part per million is a millionth of the absolute frequency. Chemical shift values are proportional to the frequency associated with B0. That's the operating frequency, 1 part per million on a 500 times 10 to the 6 hertz, that's 500 megahertz, NMR machine corresponds to 500 hertz. On a 600 megahertz machine, it is 600 hertz. On a 1 gigahertz NMR machine, it is 1000 hertz. That means differences between resonance measured in hertz are larger for larger spectrometers. Bigger magnets give more dispersion in NMR. Enough theory. I think your brain is nearly full. Let's talk about memorizing a few chemical shifts in proton NMR as landmarks to enable us to guess chemical shifts of others. Tetramethylsilane, SIME4, is a standard reference for both carbon and proton NMR. So we say that standard resonates at 0 ppm. What does the chemical shift axis look like? Well, I've already covered 13C NMR, and I've told you that delta varies between 0 ppm and around about 200, but most delta values for protons occur between just over 10 and 0 ppm. The chemical shift range in proton NMR is much tighter. Dispersions in 13C NMR are better. Here are two important terms to remember. Signals near 10 ppm at the left-hand side of the chemical shift flux are further downfield from the reference at zero than rightmost signals near the standard at high field. Protons directly attached to carbonyls, for instance, that's aldehydes, give a CH at low field, high delta, high chemical shift, around about 10. Then in NMR spectra, a little bit upfield of that are aromatic protons and alkenes, almost in the same place. Then methine CHs next to an electronegative atom like oxygen. Then methylene CH2 next to electronegative. Then methyl CH3 next to electronegative. Aliphatic methine, methylene, and methyl groups in that order, not attached to electronegative, resonate at high field, low delta values. Another NMR superpower is to work out how many magnetically inequivalent, that's different types of protons there are in a molecule. Sounds easy, doesn't it? In theory, it is. In practice, it isn't, until you've practiced a lot. And that's why there's stacks of problems about this in my e-workbook, animated with videos like this. Available on Vital Source, MacBooks, and the Kindle app. What would you predict? The tertiary butyl acetate. The answer is one slightly lower field shift for the 3 hydrogens on the methyl group because they're next to a carbonyl, and 9 aliphatic protons for the tertiary butyl group showing up at a higher field. What would you predict for methyl pivolate? One downfield shift for the methyl next to the oxygen, and 9 upfield because they're one atom removed from that electronegative carbonyl group. Conclusion: hydrogens on a carbon next to oxygen or another electronegative atom are lower field than hydrogens on a carbon next to a carbonyl, but they're both a bit shifted to lower field. It's fun, really, to make your own problems by simulating spectra in ChemDraw. And if you don't have ChemDraw, maybe you can do it in GPT, but that's a bit less accurate. Then try deducing unknown compounds from spectra and all the other information you're given. This compound has a molecular formula of C9H12. Possibly that's from high resolution mass spec. I'll do a video on that very shortly. There are only 2 resonances, one just above 7 ppm and the other just above 2. Their relative integrals are 1 to 3. That means this molecule must have a lot of symmetry because 12 protons are just resonating in 2 places. Because the relative integral is 1 to 3, and we know that the compound contains 12 hydrogens total, what integrates to 1 must be worth 3 protons, and what integrates to 3 must be worth 9. Because we're given the molecular formula, we can calculate the number of double bond equivalents, DBEs. That's also covered in my spectroscopy e-workbook, and I may do a video on that sometime soon too. To calculate DBEs, remember saturated aliphatic hydrocarbons have molecular formula CnH2n plus 2. So a saturated aliphatic hydrocarbon with 9 carbons would be formula C9H18 plus 2 is C9H20. It takes 4 hydrogen molecules to hydrogenate C9H12 to C9H20. So our unknown has 4 double bond equivalents. Acyclic compounds with 4 double bonds give many, many more proton resonances than we've got. But what if it's a ring that counts for 1 double bond equivalent, containing 3 double bonds, like a benzene. That's double bond equivalent of 4. So if it's benzene, all 3 methyl groups have to be the same. We know they're methyls because they're inequivalent. They can't be a propyl, for instance. Can you deduce the structure? I have to hurry you. Pause the video if you need more time. And the structure is 1,3,5-trimethyl-benzene. Did you get that? What about this one? It's a different compound, different molecular formula, but it looks like it has aromatic hydrogens resonating just above 7, and it's got methyl groups attached to a benzene ring resonating just above 2. The molecular formula tells us there are 10 protons. The integral is 2 to 3, so that must be worth 4 to 6. It's the only way. There are 4 aryl H protons and 6 on the methyl groups. So how many methyl groups are there? 2! The double bonds, equivalents. Well, remember it takes 4 hydrogens to convert this compound to a saturated aliphatic hydrocarbon, CnH2n plus 2. So it has 4 double bond equivalents. That again fits with the benzene ring. 3 for the double bonds in the ring and 1 for the ring itself. What do you think it is? It is... Gonna have to hurry you. Your last chance soon, unless you pause the video and try and work it out. It is 1,4-dimethylbenzene. Did you get that? Note that the aromatic protons in 1,2-dimethylbenzene or 1,3-dimethylbenzene would not be equivalent. So you see how useful it is to be able to calculate the number of equivalent protons in a molecule. If you proposed 1,2-dimethyl or 1,3-dimethylbenzene, you didn't check that. It's fun, really, to draw your own molecule, simulate the structure in ChemDraw, and then work out the assignments. Let's play Guess the Spectrum. 1. Draw the structure in ChemDraw. 2. Deduce what the number of protons is in that molecule. 3. Select the structure in ChemDraw. 4. Go to the structure command in the menu bar and scroll down to simulate 1H NMR spectrum. You get the spectrum? It lists where it thinks the peaks are. And see if you were right. How to deduce structure in 13C NMR was also covered in my video on that. 1. Draw the structure. 2. Deduce what the number of protons is, do you think? Select the structure in the menu bar, scroll down to simulate 1H NMR spectrum. See if you're right. Isn't this fun? It's not quite all though. You need to understand coupling to really understand proton NMR. Like why we see a triplet quartet for ethyl groups, even though there are really only 2 resonances. But that is for the coupling in C13 and 1H NMR videos. In conclusion, know how chemical shifts come about. Know how to define chemical shifts. Memorize a few chemical shifts that can help you estimate others that are similar. The predicting number of resonances from the symmetry of the molecule structure. Superpower. Develop that. Know how to combine symmetries, number of peaks, integrals, molecular formula, and double bond equivalents. Develop your own convenient way of putting all these together to identify unknowns. Thank you very much for listening and watching all the way here. Bye-bye now. Take care. Thank you. Ciao.